Hello and what's up to you all pre-matriculants. This is your favorite show, Physical Sciences, on a Tuesday. I hope you enjoyed your day at school. My name is Abram and I'm with John today. How are you, John?
I'm great, Abram. Nice to be with you again, grade 11s. And we're carrying on from where we were last week when we started to deal with refraction, properties of light, geometric optics. Today we're doing something really amazing.
Very exciting. I must say that there were already questions last week about reflection, so I hope the mindsetters will still give us those questions.
Well, it's not just reflection that we're dealing with. We're talking about total internal reflection.
Awesome.
T-O-T, not T-U-T.
All right.
Not your alma mater. It's T-O-T, total internal, T-I-T, total internal reflection. Very, very important, very interesting. And you know what? It's very practical. There are so many things that we use almost every day that require us to understand that total internal reflection is taking place. It's got some amazing technology and applications. And we'll talk about some of them.
Awesome. I can't wait for that. But exciting news, our mindsetters, we are having a giveaway of this awesome Casio calculator. All you need to do is to answer the questions, which are the test yourself questions. The form is on facebook.com/learnextra. And remember, we also have two links just for you for the notes, of course. One, it's the viewing link. And the second one, it's the download straight link to the downloading of your notes. Chat to me on Facebook and also follow us on Twitter @LearnExtra. Remember, we also have the challenge question that is up and ready for you on facebook.com/LearnExtra. So give it a try because John is going to give you the right answer later on.
Thanks, Abby. We're ready to get going. So what are we doing today? Let's get into it. So what I'd like to do is to start off by defining for us the conditions for total internal reflection to occur. We need to understand what total internal reflection is. I'm going to show it to you in a few seconds, and we're going to look at the conditions for total internal reflection to occur. And then secondly, I want to explain how total internal reflection is used in optical instruments. Please excuse me. So when we talk about total internal reflection, it's an application of refraction. But let's see what the challenge question is. We need to link it through together. And here it is. Here's your challenge question. How can you practically find the refractive index of a rectangular glass prism? Hey guys, that's a real brain teaser. I hope you're up to it. I'm sure you will be. But before we get into the notes and the summary and all that, let's go and have a look at some practical stuff about total internal reflection. And I hope that Wilson's going to follow me because this experiment is a little bit small, but hopefully we can see exactly what's going on. So, Wilson, what I've got here, and learners out there, what I've got is a little Perspex dish, and I hope you can see that there's some liquid in it. It's just some water, okay? So, Abby, what I want you to do is I want you to come closer. I want you to get involved in this experiment as well.
As always, John.
As always.
Yeah.
So let you hold it like that. Now, what I'm going to do, the first thing I'm going to do is I'm going to take my little laser pointer, and it's not a real laser pointer, but it shines a little red light. So I hope you can see that on my hand there is a red beam. Okay, can you see that? I hope you can you see it, Abby?
Yes, I can.
Okay, so now what I'm going to do is I'm going to shine it through. Can you see on this side there's a dot?
Yes.
And on that side, can you see there's a dot there? There's a dot there.
Yes.
So we can assume that the light travels in straight lines, so the light is passing through the water. We recognize when it goes into a different medium, it's going to change speed. But it went straight through. Now, if I change the angle just slightly, I'm going to point out that dot there. Okay, that's where my finger is. That's where the light went in, and that's where it's coming out. Now, can you see, Abby, that those two are not in a straight line?
Yes.
The light has changed direction. And if we were doing it here on the flat, you would be able to see that there's been refraction taking place, slowing down, and a change in the direction that then the light is moving. Now, here's the trick that I want to bring out. I don't know, because we're just hoping here, and I'm going to ask Wilson to give us a nod. Wilson, can you see that there's a red beam on the other side of this container? Can you see that red beam? Okay, thank you. I'm just checking with that. Now, what I'm going to do is I'm going to move the laser pointer, this little pointer, to the side here. Now, what I want you to see is if I do that, and I put my hand over there, there's no red dot on my hand. Can you see a red dot coming out, Wilson, on the camera? No, there's nothing. But look here. Look over here where my hand is. Can you see? Somehow, the beam of light has gone from this point to this point, and it's coming out over here. So what's happened, let's just put it down so that we can see if we can look at it over there. Did you see that? Okay. So it's quite interesting that if we do that, we see a little bit of light coming out there. Let's just try and get it up. Twist it again. Is this now gone off for good?
Battery.
Let's hope not. No, it looks like it's... Sorry, guys. We've had a technical issue there with the pointer. My son's probably not going to be very happy with me because I borrowed it. Okay, there we got it. We've got it again. So what we're seeing is I'm shining in on the side here, and there's a big beam of light coming out. I don't see anything coming out. We want to look over there. There's the beam of light coming out. Okay, so you can see it coming out over there. There's nothing coming from the front. The beam is coming out at the side. So what has happened? You know what's happened? Total internal reflection. The light has gone from this point to that point. It's bounced around, and it's coming out over there. Isn't that cool?
It's magical.
Okay, one last thing. And Wilson, I think you're going to have to come and look inside my glass here. Because what I'm going to do is I'm going to shine into the water from the top here. So let's give you a second or two to get there. Let's make sure that you can see. So what we're going to do is we're going to shine into the water. You can't see anything. We're waiting. Okay, he's coming. We're getting there. Just give us a second and we'll move the camera into position. So what I'm going to do is I'm going to shine the beam of water into the glass, and when it goes straight down, you see a dot on the top of the water. Can you see that? And a dot at the bottom.
At the bottom.
Okay, now I'm going to angle it. Now what we should expect is if we angle it over here through the glass, we see the dot coming out there. Do you agree?
Yes.
So I'm going to angle it into the water. Is there a dot coming out there?
No.
And what do you notice inside?
There's a dot inside.
There's a dot in the middle. So it's bounced around. So let's just watch that one more time. Let's hope that we can get it. So when I shine it straight down, it goes to the bottom. Okay? When I shine it through the glass, or I shine it through here, like that, it comes out. When I shine it at a particular angle, it goes bouncing around inside. And if I twist the glass, you can start to see that the light is coming out from the bottom.
Yes.
Okay. So isn't that cool?
It's cool. That's so cool.
That's absolutely amazing. Abby, thank you so much for being with me and for helping you get that sorted. We're going to go back to the board now, and we're going to try and explain what we've just seen, because that's the critical thing. So come with me and let's have a look at what we're saying here. So what we're saying is total internal reflection is a physical phenomena that takes place when light travels between media. And when we talk about a medium, we're talking about, for example, traveling in water, or traveling in glass, or traveling in air. What we're saying is that when a light moves from water into air, it will speed up. We know that because the refractive index of water is less than the refractive index of air. When you're going from a bigger refractive index to a smaller refractive index, you're going to get speeding up. Okay? And we've explained that exactly. What we'll see is that it will also move away from the normal. So the angle of refraction will bend away. I'm going to draw a picture for you just now so you can see. And what we recognize, therefore, is that the angle of refraction in air is bigger than the angle of incidence, which is in water. What we're saying is that there's a particular angle. There's a certain angle for every substance that when a certain angle of incidence is used, then the angle of refraction is 90 degrees. So guys, get this. Going from a medium that has a high refractive index to one with a low refractive index, that's the first condition, must be going from optically more dense to optically less dense. In other words, the light must be entering a medium in which it speeds up. That's the first condition. Second condition is that we recognize there's this particular point where refraction has, the angle of refraction is 90 degrees. So it will be along the surface of the object. In this case, we say this is called the critical angle. So we've said a lot. I want to draw a picture to show you, to help you here. So first thing, give me some blank paper or blank screen so I can draw this. And we'll come back to all that other exciting stuff. If we've got our little rectangular block, and what we're saying, please watch me carefully, we've got a beam of light that strikes, and this is, say, water, and this is air. And this beam of light strikes that position where it's going to make an angle like that. That's the normal. The angle of refraction is going to be 90 degrees. We're going to say this angle here, the light carries on there. This angle is 90 degrees. Runs along the surface. When that happens, it's moving from water, more dense optically, to less dense. So it's going from slow to fast. So it's changing its speed. Then this angle here, this is a special angle. We call that the critical angle. Okay, guys, that's incredibly, incredibly important. It is a special angle related to the refractive index of the medium. What we've got to recognize is that critical angle helps us understand that what's going to happen. If there's a beam of light that strikes the boundary between these two, and it strikes it at less than the critical angle, then we can predict, not a problem, it will go through like that. It will pass through the medium and it will undergo refraction, just like we said last week. Okay? But if the angle is greater than the critical angle, look here, if it gets to a point like that, it's now greater than the critical angle. You can see the white one is measuring the critical angle. Then what's going to happen? It's going to undergo reflection, and the laws of reflection will apply. In other words, the angle of incidence here, the yellow one, will be equal to the angle of reflection, and the object is going to, the beam of light is going to carry on moving inside the water just like that. Okay, guys, a diagram here often speaks more than 1,000 words. So I want you to think about this diagram very carefully. I'm going to move on to two other quick points in this last little bit because we'll come back to them. What we'll say, these are summarized in the notes, the conditions. The light ray must move from a greater optical density medium to one with a lower optical density. The angle of incidence must be greater than the critical angle. We've explained all that. It's in your notes. Where is this used? 3 things very quickly. The periscope, where light bounces around internally to a prism. Here, in the binoculars, it bounces around 2 binoculars, and this shortens the length. So there's total internal reflection, there's total internal reflection, and there's total internal reflection. The last one, fiber optics. Fiber optics are little glass tubes, and we can use lasers to carry data. And that's what gives us super fast internet access and transmission of data. They even use it to carry TV programs. Break it up into digital signals, and it bounces around in these glass tubes without escaping from the tube. That's what total internal reflection is about. We can use fiber optic cables to put down your stomach, and surgeons can have a look at what's happening inside you. Isn't that amazing?
So amazing, John, I must say. That's the power of physics.
That's the power of physics, and we're excited to be doing it today.
Nice one. Well, Mindsetters, the challenge question is up on the page, so give it a try. So far, there's only one person that has submitted their answer, so you have a challenge too to submit your own answer. We'll see you after this break. Welcome back, Mindsetters, and thank you for chatting with me on Facebook. There's some great comments from the Mindsetters that are watching the show and saying they're enjoying it. But a big shout out to grade 11s in Mahlabatini High School. That is from Sinamile Zesizwe and Pulani Jane saying a shout out to all the grade 11 who are watching from Khaulo Secondary School. So big ups to you guys and thank you for watching. And last one, a tweet from Rose saying, can you please holler at me and my friends? We are watching Funiwe, Faith, and Rebecca. Thank you for watching, guys. And if you're having questions, feel free to send them to us. And the challenge question is waiting for you.
And that challenge question isn't just an easy one, hey? Guys, it's a real challenge. And I want you to think about it. Get your brains working. Now, to help you get your brains working, I'm going to be giving you some hints along the way. So let's just make sure. Some of you might not have got the challenge, and I haven't got time to go over it. So where you're going to find it, you're going to go to our Facebook page. And if you just make sure that we can get this right, we can pick that one up and just move down here. You'll see right at the top of this page is the challenge question. I want to just try and get this working as right as possible. And there we go. So there's the challenge question. And said, how can you practically find the refractive index of a solid block? Okay, very important question. And you know, as I'm going onto the page, I noticed there's some other stuff here. The Casio competition is a great competition because it gives you the test yourself questions, and they're in the notes. You can be watching, you can be trying them, and then it gives you a place where you can respond to. And I want to show you that place of response. Let's just quickly go there for what it will look like. So if you click on that bit.ly, that short little code, you'll get to an entry form like this. It says, Learn Extra, grade 11, physical sciences, and it tells you that you're going to stand in chance to win a Casio calculator. I love the Casio calculator that we're using, and I'm going to give you some hints about it. So you fill in your stuff, you've got to fill in your name, you've got to fill, and then once you say continue, now in this case, I don't know if it will let me do it because it's going to require an answer from me, and I will have to just get the keyboard or the pen or something working. It's not working at the moment. You've got to fill in and then allow it to give you an answer. So if I do select, let's hope that that will do it. I'm just going to put in my name as a blank there. I'm going to put in something else there. Don't do this. Please give us the real thing because we can't send the prize to that person, as I've just indicated. And there you go. There are the questions. Now, it's really easy to answer. If you think the answer is the first one, then you can, or not the first one, you can put the answer down there and then fill in all the answers and you just tap on them, click the right answer, and so it goes on. And then the final thing you do is you fill them all in, make sure you have filled them all in, and then you push submit and it says thank you. That information is then recorded. The first person to get the most right answers will be the winner of the Casio calculator. Get your entries in. Okay.
Awesome, John. And you might as well just share your favorite part of this calculator, the functions that you
Okay,
enjoy most.
I'll get there now. You know what my favorite part is? Calculating the difference between 75,000 and 74,618. Can you give me the number? Quickly, let's do it on the calculator. Very quick. 75,000. Okay. And we can just type it in, 75,000 minus 74,618. And we just type it in like that. Don't have to worry about. The answer is 382. Now, guys, why are we saying that's a special number? Because we want you to get 382 more people to like the page. Okay? Let's see if we can, in the next hour or so, get to 75,000 likes. If you like the Casio competition, the Test Yourself competition with a Casio calculator, like the page. Tell your friends. Get some work going. Get some excitement into learning some physical science. Only 382. Remember that number.
All right.
We're going to remember it later. Now, in terms of the Casio emulator here on the board, it's got some great little features. One of the things that I like to do when I'm stuck in a question, I sometimes have to calculate the denominator. So say I get an answer of 8562 as the denominator, and I have to divide that into another number. Here's a little trick that I've worked out. Instead of like storing it and then remembering it and writing it down, if that's my answer, that has to be the denominator, I push this button, x to the minus 1. It becomes the reciprocal. So it puts it on the denominator, and then I can multiply it by 5628, and that gives me the answer that I need. Okay, so if you're stuck and you've got the denominator and you want to work out an answer, then just put x to the minus 1, make it the reciprocal, and then multiply by the numerator, and you get the answer. I think that's a really cool little trick. And it's something that I use quite often.
Very cool. And just for you guys, a fact about this calculator, it has got about 254 functions. So you might as well explore all the functions by just getting yourself this awesome calculator. 254 functions.
That's amazing, eh? Okay, guys, enough talking about calculators. Let's get back into total internal reflection. I heard and I saw on the page comments about what's that experiment you were doing. Guys, we were simply showing you, not magic, it's not David Copperfield, okay? It's not Blaine or one of those other things, okay? It's genuine stuff here. Abram would not be able to tell a lie with a straight face. He would pack out laughing, okay? So I didn't do any tricks here. That light, what you saw, bounced around. That is genuine physics. You've got to be able to understand it and explain it. And hopefully, we'll be able to do that as we look at this example. So, here we go. We've got the following question. Question number 1. And just before I do question number 1, I want to remind you something. Guys, please download the notes and work through them. Even after the show, if you didn't have them before the show, download the notes. Practice, practice, practice. Okay, here we go. It tells us the following things. It says to us, you've got a rectangular glass prism that has a critical angle of 42 degrees. It says, draw a sketch to show what happens when light moves inside the glass towards the air and strikes the boundary. So there are 3 scenarios that we want to go through very, very carefully. Okay? And I'm going to take it slowly, and I want you to tell me if I'm getting it right. You think about it as we go. So I'm going to select a little rectangular block. I want it to have that and look like this. So have a look here. We're going to allow this rectangular block now to strike the inside of the prism. We're going to strike it first of all with the angle of incidence of what value? 35 35 degrees. Now we know that the critical angle was 42 degrees. So I'm going to sketch. I'm not going to measure accurately, but I'm going to sketch, and I'm going to say to myself, let's take the green line and let's put it over there. And we're going to say, use the green line as my angle of incidence, my incident ray. And it's striking that point, hopefully there. The angle here, angle of incidence is 30. How much do we want? About 35 degrees. What we notice, the angle of incidence is less than the critical angle. It's less than the critical angle. So what's going to happen? If it's less than the critical angle, remember this is glass and this is air. So what's going to happen? The light is going to speed up when moving from glass to air, and if it speeds up, it bends away from the normal. So the light is going to travel in this direction, and it's going to bend away from the normal. Okay? Notice that the angle of incidence is small, the angle of refraction is large. Okay, that's the first diagram. You got it? Situation is glass to air less than the critical angle. So what's going to happen if we change it now? And we're going to say, let's take this whole thing and let's just redo it. We're going to take this whole thing and we're going to do the diagram underneath of what it would look like for part B. Doesn't matter how fat or wide the object is, it's just that we want to be able to see it clearly. So we're going to say to ourselves, there's the normal. Now the angle of incidence is exactly 42 degrees. What do we know about 42 degrees for this particular type of glass? Well, 42 degrees was given as the critical angle. So what do we know? We have got the critical angle. And what does critical angle mean? It means at the critical angle, the angle of refraction is 90 degrees. That means the light is going to come out, but it's going to be bent along the surface. So it's going to go like that. Okay? No, not like that. That's too much. Let's just undo that for a minute. Let's do it again. It's got to go along that surface, and it's got to stay on the surface at an angle of 90 degrees that we'll indicate over here. So this angle is 90 degrees. That angle there was 42 degrees, and 42 degrees is equal to the critical angle. Please don't abbreviate. I'm allowed to abbreviate, but in your exam, please don't abbreviate, okay? I'll get a license from Ashraf who does the accounting to abbreviate. So I understand that's what's happening. So guys, what's the third scenario? What's the third situation? When the angle of incidence is 60 degrees. Now please remember, the angle of incidence is always measured from the normal. So let's do it again. Third scenario, we're going to take our third scenario, we're going to do that, and we're going to say, here's our normal, and we're going to measure 60 degrees from this position, and we're going to put in the critical, the ray, incident ray. Notice it's bigger. That's about 60 degrees. I'm just guessing here. We're going to call this the pink one. That's 60. Now, notice that the angle of incidence now is greater than the critical angle. If it's greater than the critical angle, what happens? Total internal reflection. Okay? Total internal reflection. Okay, you've got to get this right. It's not going to refract now, it's going to reflect in on itself. What's the law of reflection? The law of reflection tells us the angle of incidence, the angle is equal to the angle of reflection. So the angle of reflection is going to be inside and it's going to look something like that. And notice here that this angle now, this angle is known as an angle of reflection, and it's 60 degrees as well. Okay, we need to be very clear that this isn't refraction, this is reflection. The light has changed its path. It was going in that direction, and it was coming out of that direction. So that's what I was meaning when I was using this little tray of water. When I shot the laser light straight across, it came out. When I did it from the side, then it was at a big enough angle, so it didn't come out here, but it came out the side. So it bounced around on the inside, and that is total internal reflection. Isn't that fascinating? Abram?
Very.
Okay, I hope you've got it, because if you've got it, then the other learners out there will have it too. So let's see if we can do one last question. I've got a couple more drawings to look at. What it tells me is to draw diagrams to show how you can use prisms to turn light through 90 degrees and 180 degrees. Right. Now, if we're using a glass prism, then we know that for glass, different substances are going to have different critical angle. For glass, we're going to take it to 42 degrees. Okay? The critical angle, 42 degrees is the critical angle. Perspex is quite similar, and we're going to have a look. So if we want to turn light through 90 degrees, this is how we're going to do it. We're going to take this triangle that is a 90, 45, 45 degree triangle. So an isosceles triangle where, stay with me, don't go to sleep just because I've mentioned angles and triangles and geometry. It's important. That length of side is equal to that length of side. Oh, that's a terrible 45. So let me just write it again. We're going to say that angle is 45 degrees, and this one is 90, and this one is 45 degrees too. So if you've got that in your head, then watch and see now what happens, how we can turn light through 90 degrees. We're going to take a beam of light, and we're going to say, let's make it hit this side with an angle of incidence of 0. So in other words, along the normal. The angle of incidence at this point, I, is 0 degrees. It's going to go straight through. Does that mean refraction doesn't take place? No, refraction does take place. The speed of light changes as it enters the new medium. But now, guys, look what's happening over here at this point. At this point, if I conduct a 90 degree angle, and I'm just sketching it, then what I hope you can see is that because this line is parallel to the bottom one, that this angle is also going to be 45. So this angle here, that angle is 45, that angle is 45. It tells me if I've got an angle of incidence of 45 degrees there, then is that bigger or smaller than the critical angle? No, yes, it's bigger. It's much bigger. It's 3 degrees bigger. So that means that the light is going to turn and it's going to come out over here. When it strikes this barrier, it's going to hit it at an angle of 0, angle of incidence equals 0. So my light has gone through a whole change in direction. Remember when we talked about angle of deviation last time, we said what was the initial angle, what's the final angle, what's the difference between them? If I took my initial angle, and I'll just finish off here, that was my initial direction, that's my initial direction, and if I measure the difference between my initial direction and my final direction, that's 90 degrees. Last little point, which is point B of this diagram, is if I take another diagram, another prism, and I allow light to travel in this direction, I can get it to change through 180 degrees. I want you to go and see what the angles would need to be for that to happen. Okay, Abram,
It's time for a break.
time for a break.
Well, Mindsetters, during this break, you still have got that chance to do the test, the challenge yourself question.
Hey, come, let's get it right.
The
Challenge question.
which is on facebook.com/LearnExtra. Because after the break, we're going to be answering it.
Absolutely.
And if you still have some other questions that are not on the challenge question, make sure that you give me during this break. We'll see you. Welcome back, Mindsetters. Now, it's good to hear feedback from you guys. You saying you're enjoying the show, and John is just the awesome teacher and the best teacher ever. We've got someone watching all the way from Zim, Ronald, saying, this is the best show ever. Keep it up, guys. Thank you so much, Mindsetter.
Okay, guys, thanks, AB. Thank you very much. There's just one thing I've noticed on the Facebook page here. Shadrach has been doing an experiment with a torch. Now, Shadrach won't really be able to see total internal reflection because a torch beam spreads the light too much. Okay, so here's my advice. He's also using a round dish. Better to try and get square sides, parallel sides. That might help. The round dish doesn't give you enough time to see the bending. Okay. Also, the torch needs to be a little bit of a finer beam of light for you to really be able to pick it up. So what I suggest you do is get a piece of cardboard, put it in front of your torch, put a pinprick through the front, and you will see much better where the light is going. Trace it out. Use your hand to work out where the light has gone, and that's really
But
demonstrating.
that looks like a glass, John.
Yeah, it does look like it's a bit of a bowl glass, but it's round. What I'm suggesting is to use something that's a little bit square. You know, even if you use an old, make something with an old cool drink bottle, stick it together. Doesn't have to be very big, and see what you can do. Okay, guys, I must say we're getting there. 6:46. Hey, that's quite close.
Actually, it's 6:52 on mine.
6:52 on yours. So we're running out of time, and we're getting up the likes. So guys, if you haven't entered yet, make sure you enter the competition because you could be a winner of a Casio calculator. So
Actually,
let's
it's 6:55.
6:50
That's James.
there we are, 6:55. Now let's go to the the challenge question. We'll see if we can come back to some of these other questions, because I know that there's some people that were really excited about this practical challenge question. So how are we going to do it? Up to you. Here we've got to take some theory that we learned last week, and we've got to try and apply it. Here is what I'm going to suggest to you. I'm going to do the theory part first and remind you that we had something called Snell's law. Abram, I'm not even going to ask you. But it basically said Ni, or N1, times the sine of the angle of incidence is equal to N2 times the sine of the angle of reflection. Now, if we are moving, stay with me, just because there's trig on the board doesn't mean you have to panic. Okay? Stay with me. If we know that we're moving from a medium, so it said, how can we work out a rectangular glass block? So we're moving from glass into air, and we want to work out the refractive index. So what we know from the lesson that we've done so far today, that total internal reflection takes place when it's bigger than the critical angle. But it helps us to understand this thing, that at the critical angle, the angle of refraction, if that's critical angle, this angle of refraction here is 90 degrees. So if I'm going to say, I'm going to move from glass into air, then what's the refractive index of air? Refractive index of air is 1. what's the angle of refraction that I want when the angle of incidence is the critical angle? Well, the angle of refraction will be 90. So it's sine 90. But hopefully you know that sine 90 is 1. We can check it on the calculator. Now, what do I need on this side? I'm wanting to find this value. So all I need to be able to do is to measure that angle. So if I can measure the angle of the critical angle, if I can measure the critical angle, or if I'm given the critical angle, so this needs to be not just any old angle of incidence. This is the critical angle, and that theta I can measure. Then notice what it gives me on this side. Let me just use the calculator. I'm going to say a sine of 90. So sine of 90, and all of you are telling me that's going to be 1 times 1, and it is 1. So what I'm going to be able to do is say the angle of the refractive index of the glass block of glass is going to be equal to 1 over the sine of the critical angle. Now, the practical part was, how do we measure the critical angle then? And here's an idea. So I'm going to use that same experiment that I drew up. I'm just going to show you how to do it practically. So let's just take our block there, and we're going to say, so when you shine the beam of light, like that torch ray that I was using, that little laser pointer, I shone it in at that sort of an angle, and I found that it bent, and it bent to about there. And at that point, I could adjust it slightly. But what I can do is I can change this angle, if I'm very patient, until it gets to the point that the angle of refraction is along the beam, like that. So I need to play with this torch, with the laser pointer, and I must get to that position. Now, all I've got to do is I've got to put a little dot over there and a dot over there, and I can then put those dots on the piece of paper, trace around the paper with a pencil. So trace over there, join the dots, construct that as a 90-degree angle, measure that with a protractor, and there's my critical angle. If I know my critical angle, I can work out what the angle of, what the refractive index of the substance is. Isn't that cool?
So
okay,
cool.
So it's an application of the theory solving a problem. There are other ways of doing it. This is just a suggestion on how you can do it with very minimal apparatus, very simple, glass block, pointer with some light going through it, some pins to measure, and you'll be able to, and a protractor, and you'll be able to work out with the refractive indexes.
I like what you just said, because I had a tweet from Rose asking what are the 3 applications of the total internal reflection.
We've done those. Remember the applications we've spoken about. The binoculars. Now, guys, before we had binoculars, we had these long telescopes. And I'm sure you've seen them in movies where they're pirates and they're adjusting things like this.
Yes.
Now, binoculars are able to shorten the length that the light travels. But the light's still traveling that distance, but it's bouncing backwards and forwards. Okay? And so it shortens the path so we don't have to have it so long. That's one application. The other is the periscope, being able to look. You don't need just to mirrors anymore. You can have prisms. And the advantage of that is if you've got a periscope and you're in the sea, what can happen is corrosion on the surface of the mirror. That's not so good. Whereas a prism isn't going to corrode as easily. So we're going to get a better image, better definition, and we're going to be able to reflect through 90 degrees twice to get the image the right way up. Okay, Abram, are there any other questions? Otherwise, I'm going to do one more of my questions.
Okay, I have some questions. Is the incident angle always equal to the angle reflection in all substance?
Okay, let's be very clear about that. So, and I'm going to go back to the question that I was doing so that we can be absolutely clear. Remember, the angle of incidence is the angle that we measure where it strikes the surface, where it strikes the boundary. So notice that in this case, this is still called the angle of incidence. I is the angle of incidence. Did reflection take place here? No, refraction takes place here. And we know that angle of incidence is less than the angle of refraction. The angle of refraction is bigger. What we recognized here, the angle of incidence is the critical angle. The angle of refraction, the angle of incidence is less than the angle of refraction. Angle of refraction, that was the incident angle. The critical angle, the angle of reflection, was equal to 90 degrees. So again, angle of refraction is bigger than the angle of incidence. So the incident angles are not always equal. But what we need to be clear about, it is always equal to the angle of reflection. Okay? That's a rule. It's the law of reflection. Angle of incidence is always equal to the angle of, this R now stands for reflection. Okay? So the angle of incidence is not always equal to the angle of refraction, but it is always equal to the angle of reflection. Whether it was total internal reflection or when light hits a mirror and bounces off a shiny surface. Okay.
Nice one. Hope that answers Thabo. Bongi says, is the critical angle always given or do we have to calculate it?
Okay. It's not always given. So like I was showing you, you could measure it. But there is a question about that I think I had, and we didn't get to it, where I actually asked you to calculate. So I've told you that water has a refractive index of 133 at 20 degrees. And I said, what is the critical angle of water? So absolutely, you can be asked to calculate. So how would you do that? Let's just quickly do that one. We're just simply going to apply Snell's law. We're going to say the angle of incidence, the angle of the refractive index of the second medium, the angle over here, and we're just going to substitute in numbers. If it was going from water to air, we were given the refractive index 1,33. So 1,33 is the refractive index. We want to find what sine of the angle of incidence, which is actually the critical angle. We know the refractive index of air is 1, close to 1. We're going to take it as 1. The angle of refraction here at the critical angle, because we want critical angle, is going to be 90, and the sine of 90 is 1. So we're going to say sine of theta, where theta is the critical angle, is going to be 1 over 1,33. And here's just my point. Remember what I said to you earlier, is this lovely trick of being able to write down 1,33 and say invert. And that's what I want to do. I want to get an answer of what that is. And then I'm going to say I want the second function of that because I want to get, so I'm going to go shift, sine, and answer. And let's see what the angle is. I've got the angle for the water to be 48,75, and I'm going to take that as the critical angle of water, 48,75 degrees. Okay, does that make sense? I hope it does.
Moving right along. Sir, can you please simplify what is critical angle?
Okay, very simply. Critical angle, the critical angle is the angle of incidence What does that mean? Incidence where it's striking the medium. It's coming in to the medium. Okay? When the angle of refraction equals 90 degrees. Okay, so the critical angle will always produce an angle of reflection that is 90 degrees. The light will not go out of the medium, it will run along the surface, the boundary of that medium. Okay, very, very important.
Unfortunately, we have.
Oh no,
Yeah.
we've come to the end.
Come to the end.
Okay,
John.
quickly, let's just check. One last thing. How many likes are we on? Quick refresh. Oh, it's not doing it. Guys, you'll have to get your friends. Go.
You can refresh.
No, it's not. It's I've got to change the thing. Let's go. Refresh.
Well, we'll see that some other time. According to me, it is 663. So well done, Mansitors. And get your friends to still like the page, share the page with all your teachers, your classmates, and everybody. But for today, we just need to end it there. And we love you. Peace.